the notification. Okay, it looks like we're live. So good morning, everyone. Thank you so much. Morning if you're here on the West Coast lunch, if you're on Jonathan's coast.
I am starting to get hungry.
Yeah, okay. And we'll keep this to around an hour, but we have a lot of questions from viewers already. And let's just start with the obvious, because I didn't get to talk to you about this yet. DART. I had interviewed you before, and that mission was a total of 10 months and 1 day. That's crazy. We were talking about how fast time is flying, but yeah, from your perspective, let's talk about DART.
Right. And so, 10 months because it had to sneak up on Dimorphos from behind. And so it went all the way around the sun as Didymos and Dimorphos were coming in to near where the Earth's orbit is. And so they sort of lined it up so that at the moment when the Didymos system was passing the Earth on the outside, about 5 million miles out from Earth, that DART would catch up with it and smash into the little moonlet Dimorphos. And at a time when also the James Webb telescope is sort of on that side of the Earth and much closer to the Earth, but still able to sort of capture the image. And so so that all worked. The choreography of all this, right, is to be very, imagine, as you say, after 10 months, right, you've got to time it so that everything's going in the right place, at the right speed, at the right time. All worked out. And so you have this asteroid Didymos and the little moonlet asteroid Dimorphos that strolls around it at about 1 mile an hour every 11 hours. Almost 12 hours. And so as it's on its sort of backswing heading in the opposite direction from the whole system, DART smashes into it at thousands of miles an hour. And that was we're waiting, okay, are we going to see anything? And wow, the images. So we got images from DART itself as it went. The thing gets bigger and bigger and bigger, right?
Wow.
And then we got images from ground-based telescopes on the Earth, particularly one called Atlas, and that showed the thing brightening, and then this big puff of stuff come off, and then we got images back from this little Italian probe that DART ejected about a couple weeks before the impact, and so LiCube flies sort of a little behind DART and sort of a little to the side. So it's about 30, misses the Didymos system by about 30 miles. And it's going 500,000 miles a day, right? It's going, so it passed through the system about a minute after the impact and had just like a couple of minutes to go click, click, click to see what was happening. And managed to get these close-up images, these incredible streamers and coming off of the impact. Clearly, a lot of stuff got kicked up by the impact. You look at those images and you thought, okay, that really hurt, right?
Yeah.
And very interesting that we've seen this as well on a couple other asteroid. I'm blanking now on where else we've seen it, but a couple other asteroid impact kind of scenarios, and not on when you just do an experiment trying to make craters like in the lab, smashing into some piece of rock or something, though, you tend to get a much more even splash. But when you do it on real asteroids, you get these rays coming out where instead of, it's like, instead of a uniform thing. And so apparently, according to one of the experts on this kind of stuff is Phil Metzger, and he says that it's something called granular collapse. And there's some way that if all the boulders are roughly the same size, it tends to self-organize. The way that they hit each other tends to cancel out, sort of, it tends to group them together, and you get these jets. It's some interesting physics. The physics of lots of little pebbles all together interacting with each other turns out to be complicated and interesting, and we're learning about that through studying these things. So that's one thing, but it doesn't give us the big answer. And the big answer that we're looking for is, how much did we change the speed of what's left of the moonlet?
Right.
And how much of the momentum went into shoving things off, how much went into actually shifting the moon. And you're not going to be able to measure that now, because the brightness of all the stuff coming off it is sort of blinding us to what's actually happening on Dimorphos itself. So we're going to have to wait till that settles down, and then over the next months, probably, maybe just weeks, but probably months, we're going to just measure the brightness. So when you look at this double asteroid system from Earth, you can't see the separate asteroids. They're too close together. You just see one bright spot. But the orbit of Dimorphos around Didymos is such that it goes, as seen from Earth, some of the time it goes behind the bigger asteroid Didymos. Right. And when that happens, the combined light decreases. Right, okay. Didymos blank, sunlight's bouncing off both, but the Dimorphos light is blocked by Didymos. It's eclipsed, and so you can, if you sort of do brightness versus time, you see a little dip when the little one goes behind the big one.
Yeah,
and you can measure the time of that dip. I mean, you can see that if there isn't all kinds of other crap happening in the system like there is right now, right, because you smashed it up. But once everything's settled down, you'll be able to see that dip. And every time that dip happens, right, you've got a measurement of how long it takes Dimorphos to go around Didymos. And the expectation is that instead of taking 11, hello cat, instead of taking 11 hours and 50 minutes, it'll only take 11 hours and 40 minutes because DART smashed into the thing and slowed it down a bit.
Right.
And so that's a pretty easy thing to measure if you can measure the time at all, right, is a difference of 10 minutes. We can measure times to much higher precision than that. And so even on a crappy sort of light curve like we're going to get from this asteroid. And so it should be, once things settle down, it should be pretty easy to determine the change in orbital period to pretty high. So that gives us a measure of, it's sort of this basic high school physics, right, of A hits B, little thing going fast hits big thing going slow, and you conserve the momentum. But because they're squishy, there's all this debris coming off, it's not quite as simple as that. And so there's a fudge factor. And that fudge factor, which we call beta, is some number between 1 and 2, that probably, or maybe 1 and 3, maybe, that's sort of a fudge factor that says how efficient was DART in actually pushing Dimorphos. And so the different scientists are basically putting different bets on. I think it's going to be 1.3. I think it's going to be 2.4. And that's the number that we're looking for to say, do we understand the squishiness of the asteroid, the how well an asteroid gets pushed when it gets hit. And so that's the sort of scientific part of the measurement, as opposed to the engineering stuff, which is equally important, which is, can you do the automatic homing in targeting and actually hit the damn thing? Or are you going to embarrassingly, whiz on past, missing it by half a mile or something, which was not ruled out, right? I mean, they thought they'd done it right, but it's not, just because they made it look easy doesn't mean it was easy.
Right. And that kind of reminds me of, timing and precision being so important, obviously, with James Webb, but how important was that also with DART? And were there any concerns? I know that you were concerned about, things with Webb. Were you concerned about DART not being successful?
I mean, I wasn't super concerned. DART had a lot fewer things to go wrong with it, But the main thing is, so they have you've got to have all the critical things go right in like a 1 hour period,
right?
Right, as you get in there. And in particular, the thing that's maybe a bit sporty is this automatic targeting system, right?
Okay.
Where it's got to see Didymos, it's got to see Dimorphos, the much smaller, fainter object. It's got to then lock on to Dimorphos and control its thrusters so that it keeps Dimorphos in the center as it goes in, right? And you can imagine, like, if your camera wasn't quite as good as it ended up being, if the image was fuzzy, you might get confused as to which was Dimorphos and which was Didymos, or you might not be able to see Dimorphos at all. And so then you could end up not being able to target on it. If Dimorphos ended up being a really weird shape, that could confuse the algorithm, right? And so, or maybe the thrusters just decide not to switch on that day, because that's happened in, like, plumbing goes wrong sometimes in spacecraft, right? Yeah. It's and you can't, no time to call the plumber. So and so there are certainly things that could have gone wrong, right? And so that's, test for that before launch and all that. But yeah, it wasn't. It was all pretty, like, we were pretty confident, but you never know, because sometimes things, sometimes you don't build things right. And right. or that, there's some, you could imagine, for example, that if there was a lot of dust around the asteroid because some other mini meteor had hit it or something, right? That dust could reflect sunlight, and that could confuse the cameras. And so there could be, the environment isn't quite what you expect. It wasn't what you designed for. And so then, the thing doesn't work. So there are always, so the fact that it worked flawlessly and as expected is both a testament to the engineers and also a bit of luck that, yeah, we guessed right about what the physical environment of this asteroid was going to be like.
But regarding, like, the streamers and the tail formation, you say you have some theories, but we're still kind of investigating that.
Right. Well, I don't have theory. I mean, Phil Metzger has theories, but yeah, this is not my field. But I think it's my level of understanding is that, yeah, there's really interesting physics that we're starting to understand associated with these objects that are really not worlds like the Earth, because they're what we call rubble piles, where there are sort of lots of little rocks that are held together by gravity, but not really, it's more like a ball pit, right, in space, held together by gravity. And so it's very smushy and it's easy to throw things off. And how that behaves when you hit it is something we're still learning about. And so that's really nice. It's because, and one of the reasons it's really nice is because it's critical in the formation of planets like the Earth. Planets like the Earth start off with a lot of things like Dimorphos clumping together to make bigger and bigger things. And our gaps in the understanding of that process when you're still at the stage of getting the little things into slightly bigger things is one of the key gaps in our understanding of how the Earth came to be and how other planets came to be. And so we're really, it's not just about asteroid defense here. It's also about solar system formation and stuff like that. There's lots of great science to be done.
Well, I did gather a few questions on Twitter. I'm still waiting for people to ask in the comments. So when do you think we'll get an article released about TRAPPIST-1 using James Webb Space Telescope spectroscopy tools? Someone wants to know.
I haven't been following Webb looking at TRAPPIST-1. It's looked at a number of exoplanets. I've been impressed by how fast some of the early James Webb papers have been coming out. We have this thing called the archive, arxiv.org, on the web, where all of the papers sort of come out first before they're published in the journals. And so every day, we see a few more James Webb results come out there. And normally when you do an observation, it can take 6 months or a year to publish your results. And clearly for these first James Webb observations, everyone's been like really trying to push them out really fast and get early papers out to scoop everybody else. And so we may see something, in the next month or two, but it's hard to tell. Give the guys the time to work,
Yeah, seriously. Omar wants to know, when will we start mining asteroids and other planets? I feel like I get this question a lot, actually.
Right. Well, in a sense, we've sort of kind of started in the sense of, Hayabusa 2 brought back a little piece of Ryugu, and OSIRIS-REx is on its way back from asteroid Bennu with a little bit of ore from Bennu that it collected. And those are, really scientific missions, not like let's get the ore and sell it missions.
Yeah, we want more than just a little.
Yeah, right, exactly. Yeah, no, but it's baby steps, right? And so we're at the point now where we've shown what you learn from these missions, right, is exactly more of this granular physics, right? We were really surprised with OSIRIS-REx when the kind of drill thing went into the surface. It went much further. The whole spacecraft almost got swallowed by the asteroid because the asteroid was so smushy. All right, and so you need to do a few more tests like that before you can even design your proper asteroid mining spacecraft, right? Because you need to know what kind of drill you need and what's going to happen when you start drilling in and so on. And so there's that, and then there's finding the right targets. There's still not that many targets we know that are. You need to have two things, right? You need it can't just be any random asteroid. It has to be an asteroid with a lot of valuable ore, right? So, for example, there's a mission called Psyche, which just got delayed, but it's going to visit this asteroid that's mostly made of iron instead of rock, and so that would be the first time we've visited one like that. And you've got there are various techniques like spectroscopy that you can use to sort of pick out the good asteroids. So there's still a lot of surveying to do, just like when you're a miner on Earth, right? First thing you do is you send the geologists out to survey where the good mines might be. We're still in that phase for the asteroids, picking what the good ones are, the ones that are both easy to get to and high value.
Right.
And there aren't that many of them, it turns out, that are really easy to get to and really high value. And so, and then you got to just have a robust system that's going to be able to get a large amount of stuff back. Yeah. And we're not quite at that point yet. We need to try the sample return from something like the Psyche asteroid, one of the metal ones. We need to practice a bit more. So I think the first generation of asteroid mining companies that have all gone bust now, as far as I can tell, were a little premature, but it'll come. Right. And so I think I would guess we're talking more 2040s than 2030s.
Oh, wow. Okay. All right. We're taking bets today. Alan wants to know, I'm interested to know what Jonathan believes is the next step in asteroid defense. What now?
So let's be clear about what happened with DART, right? Let's assume it's successful, we get the result we expect, which is that we changed the motion of this rock by a millimeter a second, which is roughly 30 miles a year, right? And so if you get 10 years warning of an asteroid like Dimorphos heading toward the Earth and you send DART to hit it, you'll have moved its, over 10 years after you hit it, it'll have moved its impact position by like 300 miles, which is not enough because the Earth is, 4,000, is like, 5,000 miles across or whatever. I'm sorry, I don't do miles. It's 12,000 miles. So you need something, and that's okay. It just means you need to build something bigger, right? It's once you understand the physics, once you measure beta and all these things, there's just a question of scale the thing up. Not quite, because you don't want to actually destroy the asteroid. That's another thing. So you can, maybe you need to send 10 DART probes or something like that, right? To move it enough. So you could do that. You could build like 20 darts and fire them so they all arrive, a week apart. And then when you've hit it 20 times, you've moved it enough that it's after 10 years, it'll have missed the Earth. So I think we're, like the proof of concept is there, right? But that's a long way from having an operational system.
Right.
And it's, one asteroid, but as we've just been saying, there are different asteroids with different, makeups. And so maybe it's, maybe you need a different kind of defense mechanism for different kinds of asteroids, right? There might be asteroids where this hit it hard with a rock thing doesn't work as well. And so I think we need to try missions like DART. The next big step, though, is a continuation of the DART mission, which is a European mission called Hera.
Okay.
And Hera is going to go back to Didymos and Dimorphos a few years from now, after all the dust has settled.
Yeah.
And go back and do really detailed imaging, not the little fuzzy images that we got from Licia Cube, but more like that last image from DART where you can see all the pebbles, right? And so look at the crater that DART made and really understand exactly what it did. And so that'll be fun. We'll get some really nice pictures of the dent that DART left in Dimorphos.
Here's kind of like a follow-up question to that from Glenn. He says, as we do more of these impact redirect experiments, how difficult do you think it would be to accidentally put one on an Earthbound intercept? Pretty hard.
Impossible, yeah. And so the thing is this, right? You specifically pick your target so that although it's close enough that you can observe it nicely from Earth, its orbit is different enough from the Earth's that however much of your energy gets transported into moving the asteroid, it's going to be tiny compared to what you'd need to put it on an Earth-hitting trajectory. And so if you think about DART at Didymos, worrying, okay, could it accidentally hit Dimorphos in such a way that it makes it hit the Earth? It's sort of like saying, if I have a plane crash in London, is some of the debris going to hit New York?
Right. Okay.
Well, no. Right. It might be, depending on how big the plane crash is, it might be, a mile or 2 miles or something that you got to worry about, but it's not 5,000 miles, right? And so that's sort of what we're talking about here. It's like, no, there is no, however badly you screw up, right? By smashing something into the ground in London, you're not going to affect New York. And so however badly you screw up at Didymos, you're not going to risk any of that stuff getting to the Earth.
Good to know. Good to know.
And there just isn't enough energy to have anything significant get anywhere close to an orbit that would intersect the orbit of the Earth. And so, a few million miles is, safe enough. But it's a good question. So obviously, right? I mean, before you do an experiment like this, one of the first things you say, let's not make things worse. And so that's part of selecting your target, is making sure you don't do something really stupid like that.
That's good to know. Good pre-planning. This is a Twitter question. Someone wanted to know, and if you guys don't know, Jonathan's been tracking satellites since what, 90, 91? Around there?
1975, maybe.
I was wrong. They want to know when and what started.
On the Webb since 1989.
Okay, so I was close.
Yeah.
They want to know when you started tracking and why you do this.
Yeah, well, to be clear, in tracking, I don't actually go out. Mostly, I don't go out and actually observe myself. I let other people get the data. So keeping track of is maybe the more accurate saying is like being the chronicler, right? And so, and I see hi from the UK from Mark Bird. I was going to mention that part of it is that I grew up in the UK. So when I was 8 years old, my dad, who's a physicist, spent a year at NASA, Goddard Space Flight Center in DC. And so I went over to Goddard for a year. And as an 8-year-old, I was running up and down in the corridors of NASA, annoying the scientists and engineers. And that was the year before the moon landing. And so that was, an amazing time to be an 8-year-old at NASA. And then we went back to England, and I was really frustrated because the English media were really not that interested in space, and did not cover it well. And so if I wanted to keep up on the nerdy details, I had to learn how to do the research myself. And so I would go up to the Science Museum Library in London at the weekends and read Aviation Week and read other, dig into conference papers and things like that as a 13-year-old to kind of make my lists of, so I found this list. Actually, I remember very clearly, I was probably about 12. There's Jane's All the World's Aircraft, which is this compendium of airplanes, but it has like spaceships in the back at those days. And they had a list of like this year's satellite launches, and I copied it out, there. And then I was very disappointed because it became very obvious to me pretty quickly that it wasn't that great a list, that it wasn't complete, and that, there were things, it just wasn't, you could do a better job, right?
Right.
And so 13-year-old me says, okay, I got to start doing a better job. I'm going to make my own list.
Oh my gosh.
And here we are decades later. And now I have the best list. And so that's pretty much how it happened. And I spent, when other people were like playing sport and things, I would go to a library and find old space stuff. And yeah, they are still like that today. And copy out details of some obscure rocket and build up my files. And I had handwritten index cards, right? And then at some point I typed them all into a word processor and into a computer. And so that sort of propagated down to the website that I have today. So yeah, it's been a ride. And as part of that, it's fun because you get what I like about it is it gives me an excuse to go down all kinds of different rabbit holes.
Yeah.
When Iran launches a satellite, so now I have to sort of become at least marginally familiar with the Persian alphabet and some of that cultural stuff, right? In order to be able to even use Google Translate to make sense of what the Iranians are saying, and I got to in terms of trying to find exactly where all the launch pads were, I've got to go visit some of these launch sites around the world.
Yeah, you have. Yeah.
In French Guiana, in India.
Yeah.
And so it's like it's sort of an excuse to kind of go discover different things in the world. Space is connected to so many things.
You've traveled a lot, and you're also a polyglot, right?
Well, I wouldn't say that. I mean, I'm a multilingual, but I have I have pretty good English, American, and French, and kind of crappy German and Russian, and excellent Google Translate skills in everything else. and so I'm not one of these people who speaks 15 languages fluently or something,
right.
but I do like language, and I like learning, and I like, I think you have to do a certain amount of that to get into the cultural mindset of a particular country, to understand what they're saying about their salut frangien.
Well, yeah.
And so it's, I think that's important because if you're only Anglophone, then you I think you miss you miss a lot of nuance in what other countries are saying about what they're doing.
Well, I just remember when Tim Dodd was telling me in our interview that he had to hire a bunch of like Russian translators as part of his research. You were telling me you have all these books in Russian and you can pretty much work through them, right?
Yeah, I mean, you know what, my Russian, you give me a piece of Tolstoy, I'm lost. But you give me our Rocket Space Corporation Energia document and the vocabulary there that I'm good on, you know, and so oui, merci, Florian. And so yeah, so it's this very specialized vocabulary, but I can make sense of it and I can get through to the key point. Well, first you look for the numbers, right? That's what I want. I want the numbers. And then I look for the words around the numbers that are going to tell me what the number really is.
Right.
And so it's like, okay. And when you have, you know, something like orbitalnaya stanция orbitov perigee, you know, which is orbital stations orbit at perigee, right? 432 kilometrov. You know, that it's not too hard, is what I'm saying. It's often it's not too hard to guess your way through a lot of it.
I just think languages are fascinating. So, yeah, but let's take another question from Twitter. Someone said, if someone wanted to be a world-class science communicator, does Jonathan think it's better to become a communicator or scientist first? And is it possible to learn both at the same time? What if it isn't?
Wow. Okay. Oh, I gotta be careful here. You've basically set me up to alienate exactly 50% of my friends.
Oh, no.
That's what I give, right? You know, I think there are great science communicators of both kinds. I personally feel like there is a certain advantage to being a practicing scientist, or to having been a practicing scientist, to really and several things. I mean, what it gives you is, if you've actually published papers yourself, if you've participated in conferences, if you've participated in scientific arguments, you have a better sense of when people know what they're talking about and when they're bullshitting. And also, when you ask other people for information, that, I'm going to say, that PhD behind the name, you know, helps open doors and helps people respect the questions that you're asking. They know that you have some clue, right?
Right.
But there are, you know, and yet there are communicators I know who, even though they do not have a PhD in astrophysics, are like scary to me in how good they are at understanding the papers and understanding the astrophysics and being able to go one-on-one with a sort of professional scientist. And so it's clearly, it's clearly not required. But I do think I think you need a mix, right? And my own trajectory here was that I think in astronomy, as opposed to aerospace engineering, right, there is much more of a tradition of outreach being part of what you do.
Right.
And so as a 15-year-old, I was giving talks to my high school astronomy club, right? And I gave my first BBC radio interview when I was a graduate student, and so about 24 or something like that.
Wow.
And TV as well around the same time. And so I've been doing TV and radio since my early 20s. And
you've been doing a lot of TV lately.
I'm doing a lot more than I did in those days. Yeah, but as I say, it's something that comes with practice. Mm-hmm. but it's not so much the TV and radio as the public talks to high schools, to astronomy clubs, to retired people's groups and things like that, right? That we do as astronomers a lot to spread the word. And because, the taxpayer mostly pays for astronomy, all right? And so we feel an obligation. And part of our job is not just to make the discoveries, but to communicate the excitement of those discoveries to the people who paid for it.
Right.
Right. And so I've been doing that, since I was in my teens. And so you learn when, the things you say that make people's eyes glaze over, the things you say where people get it more. And so you learn how to cast it in a way that, and it's tricky, right? Is you want to cast it in a way that's simple enough that people can sort of get the point of what you're trying to get across without misrepresenting.
Mm-hmm.
And, as a trained scientist, the danger is always that you're so uptight about saying something that's not 100% right.
Right.
Right. That you have to make it so complicated that then you lose everybody.
Totally.
And so you have to be prepared to say things that are like maybe not 100% right, but get
the
like
idea across.
Right and get the idea across, right? And finding that balance that you're not like really misrepresenting things, even if it's not quite right, and that you're not going to have the smart ass kid in the audience who goes and says, "No, that's not right." There's always one, right? And I remember I was that one. And so that's been a really nice adventure, and I think that it's important for every scientist. I will say this: whether or not the best science communicators are communicators first or scientists first, I think it's really important for scientists to communicate with the public, especially in this era of fake news, and the science is really important to people's lives, and they need to understand it better.
Oh, the era of fake news? You don't say. I've never heard of it. Never experienced it firsthand as a journalist. I'm just kidding. Right. Anthony wants to know, what are your views on Neptune and Uranus? Maybe he just they seem to be neglected in research.
Right. Well, I have friends who study those planets who would thoroughly agree with you. They've been clamoring for a mission for a long time. I can't remember what the latest is on selection of that mission, but they're hard to get to, right? We were lucky in 1977 when we launched Voyager. Once every 150 years, the planets line up in such a way that you can bounce the probe off Jupiter and Saturn to get it to Uranus and Neptune quickly, right? And so Voyager 2 was able to do Jupiter, Saturn, Uranus, and Neptune in a 12-year period, a thing called the Grand Tour. And that was, but you won't be able to do that again for another 150 years or so. And so, but you can do, go to Jupiter, bounce off Jupiter to get to Neptune. Something like that. You just won't be able to do the whole set. And so, but still, it's going to take, it takes years to get to the outer solar system. And what you really want is not a flyby, but an orbiter. And that's much harder, because then as you're passing Neptune, say, you've got to fire a big rocket engine to slow yourself down and get captured into orbit around Neptune. So that requires a much bigger spacecraft, and therefore a much bigger rocket back in the beginning to get you there. So I think scientifically, there's a lot of interest in pursuing outer planets missions, but technically it's hard, and so it's when they come up against yet another Mars mission, right, where the public is so, oh yeah, let's go to Mars, right? Then it's hard for them to compete. But I think it's time. I think it's time for a mission to study these outer planets again, and I think we're going to get one. I can't remember if one's now been selected. That's embarrassing. Let me just.
It's all right. While you're looking at that, I want to say big thanks to these amazing super chats. Ed says, Jonathan, you made me laugh. Ellie, thank you. You know I love your show. 100,000 subscribers soon. We're hoping it's growing rapidly. And let's see, JMR's desk, $100 super chat. Wow, that is a great way to start off this Monday. They say, always enjoy Jonathan interviews. Thanks. So again, these super chats really mean a lot to me. I've been doing a lot of traveling for the channel, as I'm sure that you have seen. And so these directly are contributing to that and getting better content. So just thank you everyone for watching and the super chats. And people really like you, Jonathan.
Oh, thank you, Ellie. That means a lot to me. It really does. And yeah, so the Uranus orbiter and probe mission is a study that was, I think, endorsed by the decadal survey that sets priorities. But I don't think it's actually been, I don't think it's actually been funded yet. So I think there's moving, the community is moving in the direction of, okay, yeah, we're going to do an outer planets mission. It's going to be Uranus. It's going to have both an orbiter and a probe into the atmosphere, and it's going to be maybe in the 2030s. So I think that's what I would look forward to. And I absolutely agree. It's time. It's time to go back there. We need to look. Also, they have these moons, right? Which, like the moons of Jupiter and Saturn, might have underground oceans and things like that, right? They're going to be mostly made of ice, and so both scientifically interesting and interesting in terms of origins of life questions and stuff like that. And so I think there's a lot of science to do out there in the cold outer wastes of the solar system, and it's time to go there. I know Heidi Hamel, for example, at MIT, is a senior scientist who's very interested in that kind of stuff. And,
so much science
at some point.
So much, just not enough money, right?
Well, it's not. I mean, we always say compared to things like the defense budget, it's tiny, right? But yeah, the amount of money that is in the space program budget, not enough. I love my shirt too. Thanks.
Everyone loves your shirts. They like your shirts.
So it's a question of again, it's very important for the public to make clear to in polls, but also in talking to politicians and so on that we really think NASA should be supported, or if you're in Europe, ESA should be supported, and that funding for these missions should go ahead. I mean, one thing that's interesting, the one thing I've been talking about lately is how the inner solar system, Earth, Venus, Mercury, Moon, whatever, is sort of home territory now. And there's all these different countries exploring it. We have a United Arab Emirates probe in orbit around Mars, right? We had an Indian one, which sadly just announced came to the end of its mission. There's a Korean moon probe just on its way to the moon right now, and there's starting to be commercial activity in the area of the moon, and so there's a lot of activity by a lot of different countries in that area. But the outer solar system, the asteroid belt and beyond, Jupiter, Saturn, Uranus, Neptune, Pluto, and beyond, that is still superpower territory. It's still U.S. territory, basically, and a little bit of Europe. And so it's still the frontier, right. And so we need to be at the frontier. We need to be doing more out there.
Before I forget, because I was just in Florida for what I thought was going to be a SLS launch. So we all saw what's going on here?
It's frankly, it's embarrassing. And here's why. So the idea of SLS, which is nicknamed the Senate Launch System because its design was so constrained by the political side and not by the engineering side, is okay. We're going to do this very expensive astronauts to the moon thing, so let's reuse hardware we already have. And so we're going to take the engines from the space shuttle. We're going to take the solid rocket boosters from the space shuttle. We're going to make a core stage that's kind of like the shuttle external tank, but not quite the same. And then we're going to take an upper stage from the Delta IV, and we're going to sort of put all those together. And so that'll be cheap, right? That'll be easy because it's all, stuff we already have, kind of, except everything is slightly different. It's not just reused. And somehow they managed to make it so expensive that they couldn't afford the level of testing that you really want. And I want to contrast that. And so having the problems we've been seeing lately, not counting hurricanes, have been, this leaking hydrogen stuff.
Right.
And it is true that hydrogen's tricky stuff and it likes to leak because it's such a tiny molecule, H2, that it gets out in much smaller gaps than other molecules can get through. But look at the European Ariane 5 rocket. The Ariane 5 also has a massive, big liquid hydrogen engine in its first stage. They never have these problems. They've been flying it since the 90s. And what they did, I'm told by the Ariane folks, is that they built a whole tanking test vehicle that was like a dummy Ariane 5 that had all the plumbing. And they spent, while they were building the first Ariane 5, which admittedly blew up, but that's another thing, they spent 2 years at the launch pad tanking, detanking, fill it up, drain it, fill it up, drain it, figuring out all the bugs and the leaks right in the ground system. And so they spent that time in a way that the public didn't notice, right? Because it was just a tanking test vehicle and not trying to launch. Right. And they did it properly. And so when the first Ariane 5s rolled to the pad, they never had these problems. And I think that's, so it's not that liquid hydrogen is impossible to work with, right? It's that I'm afraid, this team, who in many ways are fabulous, this SLS team, don't know how to work with it or haven't been allowed to take the time to get the bugs out of the ground system. Right. And maybe, they've done a lot of testing of the flight systems, but the ground equipment that's fueling it, they haven't had the same liberty to spend money on testing it thoroughly. And so I think that's just embarrassing that it was foreseeable, because for 30 years they had these leak problems with the shuttle and they kept on having them, right? So it's not like it's a huge surprise, and it's a different system, but it clearly isn't debugged enough. So I'm concerned about that. I'm concerned about what it says about the overall management of the program. That when that's so bad, what else is there in the system that hasn't had the right kind of attention?
Well, I'm curious from your perspective, because this is kind of like a running bet now, and it just keeps changing. Which do you think is going to launch first? SLS or
SLS? Yeah. SLS on a Starship on an orbital attempt, or SLS, right?
Come on.
I really have no idea. I will say I don't expect either of them to fly this year.
Wow. Okay.
I would say early next year for SLS, because I think we're going to go back to the pad in November, and we're going to have another leak situation or some other thing is going to happen in the countdown, and they're going to scrub, and then now you're into December, because each time you have a major problem you have to wait till the next window.
That is not optimistic.
So maybe December. SLS could go in December, maybe, but let's say it certainly wouldn't surprise me if it slips into the new year, especially as the weather gets worse in Florida and things like that. And Starship, I have no idea how close they really are to doing that orbital test. I mean, Elon says November, right? So if you make the Elon time correction, that's probably February.
What do you think about that conspiracy, though, that, there's just no way that because the government won't let Starship launch before SLS? Do you think that there's any merit
No,
to that?
I don't
No
think
way?
that's that level of coordination.
Okay. Because a lot of people suspect that, but I just...
Yeah, I don't buy that. I think there's absolutely legitimate concern for the environmental impact statements and things like that, and the licensing. I think that on the other hand, I also think that the FAA and so forth are too slow in their processes, not well matched to the current let's go guys of the commercial space industry. And so there's some, you don't want to be fully matched to that because, the commercial space industry are always going to want to go, all right, let's go now. And it is a legitimate function of government to go, just a sec, guys. Let's check that you're not going to screw other people over when you do this.
Yeah.
Right. And so that, that takes some time to do the due diligence, but does it really need to take this much time? And so I think there's going to be an evolution of this where as there's more experience with these kind of things, the processes are going to be a bit streamlined, but they're always going to be slower than the commercial space people will want. Right?
Well, speaking of, another launch, Anton's World of Video says, my son is 12 on October 6th. Hopefully Crew 5 launches without incident that day. I was actually supposed to go to the Crew 5 launch. It was delayed. And then, I thought maybe I should go to AI Day instead. And I'm glad because, I met Elon and stuff. But do you think that Crew 5, considering the weather right now, do you think there will be any issues with that?
There's always possibilities you never know with the weather, right?
Yeah.
So I have confidence in the Falcon 9 Dragon launch system, overall system. So I'm not particularly concerned with when they light the thing. I'm pretty optimistic that the launch will go well. But that's because you check everything on the countdown and you look at the weather and so on. And so, there can be a valve that's out of spec. There can be, something on the last launch that when you're reviewing the data, you think, that looks funny. Don't quite understand that. Let's stand down and look at, make sure it's probably nothing, but, let's do the analysis and that'll take a few days. Or it can be, another hurricane coming through. And so you can, that's the nature of the business. You can never be sure that it's going to go on a particular day. And I'd much rather it be that way than go fever, right? It's much better to launch your many $million rocket when you're confident that it's safe, as reasonably safe as it can be.
That reminds me to ask you this: would you feel safer being launched by SpaceX or Blue Origin, considering that recent anomaly that we saw?
Right. Well, okay, they're very different systems, of course, right? Blue Origin is a suborbital system, and so it's actually much less stressing is much less pushing the envelope than a Falcon 9 launch to orbit. So I'd probably actually feel safer on a Blue Origin, to be honest.
Really? Okay.
The emergency escape system worked perfectly.
Right.
Yes, they do tests, but this was one where it's one thing to do a test where you're setting the system up, you're going to use the escape system. It's another thing to have a regular launch where you're not expecting to use the escape system, and the sequencing of, we see the problem, now it fires, and yes, it did what we told it to. That actually gives me a lot more confidence in the New Shepard system. It's like, okay, good. The escape system works as spec'd in a real life situation. Right. And so there was no one on board, of course, on this flight, but if there had been, they'd have been okay. Right. And so I think so I have pretty good confidence in the New Shepard system.
Yeah.
I think the big issue with Blue Origin is when the hell is New Glenn going to fly? I mean, it's if my Amazon package had taken that long to get there, I'd be wanting to go back. So, and then Falcon 9, my only reason for less confidence is just that it's a much more dangerous thing to try and do, to go to orbit, right? Much faster velocities, much higher energies. And so of the systems that go from Earth to orbit with people, I would say Falcon 9 is currently probably the safest.
Okay. Yeah.
I mean, there are two, right? Three actually. There's the Soyuz and the Shenzhou, and both of those they're all pretty reliable, actually.
I still feel like it'd be so scary.
Oh no! Well, and that would be an appropriate reaction. You remember what John Young said about this, right? Which is, anyone who's sitting on top of that much liquid hydrogen and liquid oxygen on a system that was all put together by the lowest bidder and ain't nervous, don't understand the problem.
Oh no! Oh my gosh!
That was when he was on one of the space shuttle test flights. But the sentiment, applied. He was one of the, ice cold, right stuff, Gemini Apollo astronauts, right? But,
oh my gosh! And that's a great point with the lowest bidder.
Yeah, if you ain't nervous, you don't understand the problem, right? And the physics of you're in this explosive mixture that is, that is going to propel you up through the atmosphere. This is, it is not a safe hobby.
No, and it's not cheap. Rodney, I want to say thank you for the super chat. I'm so glad that you were enjoying the interview. And I'm also really glad that I have you guys to remind me of these questions, because how can I forget? Hubble orbit adjustment mission should be very, very interesting. How we have to talk about that. There's so much going on.
So Jared Isaacman, who flew on, who funded the Inspiration 4 mission and flew on it, and is funding the Polaris missions, tourist missions on SpaceX, wants to go up to Hubble and boost it back to a higher orbit.
Right.
And now this is, to be clear, this is not an approved mission at this point. This is an approved study.
Okay. That
NASA and Jared's team are going to get together and study this to see, how this would work and whether it would go. So this is like money for a study, not yes, let's light the touch paper and go, right? And so it's not necessarily going to happen. But I think the feeling I'm getting from this is that NASA are really interested in doing this, and it's certainly the case, right, that as Hubble's orbit slowly declines, it's still like 500 and something kilometers up. It's got a few years yet, but we're coming through solar maximum where the atmosphere is dense. It's going to come down faster and faster. In the next 5-10 years, you're either going to have to deorbit Hubble or reboost it. The argument against reboosting it is a lot of its systems are old. And so if it dies on you while it's up there, then it's much harder to remove from orbit because it might be tumbling and so on and so forth. So, if I were like a cover my ass NASA manager, I might want to go, you know what? It's had its run. Let's be safe. Let's go up to it. Instead of boosting its orbit, let's just dump it in the ocean. And that way, nothing can go wrong after that, right? And that's what they did, for example, to the Compton Gamma Ray Observatory back in the year 2000. Was working just fine, but the cowards in charge at the time decided to cover their asses and get it out of orbit. So I'm actually encouraged that this is, NASA's now maybe a little more brave and going, we think it's going to be work enough. The worst that's going to happen if we reboost it is it might go into safe mode. We can still have it in a safe orientation where we could go up and deorbit it. Will the cameras keep working for another 10 years, right? So it's a trade because, if if you reboost the orbit, but the cameras all die, maybe you don't, or maybe you only get 6 months science out of it instead of another 10 years. If you get 10 years more science out of it with the current cameras, which is entirely possible, I think. There's no reason to think these things are going to break right now, except that they're all really old, right? Then that seems like that would be worth it. And having private industry come up with that solution is a really interesting way to go. It's sort of, it saves NASA some effort. It also provides Polaris and SpaceX with this capability that they can now offer to, for example, communication satellites or something like that. And so the worry is, it isn't clear to me that the Dragon is well matched to this problem. In that they don't have a robot arm, right, like the shuttle did. There's nowhere to really dock on to Hubble. So there's gonna have to be some specialized hardware. And I'm not really comfortable with Dragon like kind of station keeping with Hubble as the astronauts, because then you've got all of these rocket jets firing chemicals that are going to go on the Hubble mirror and contaminate it. And so, there's a lot of basically, don't get your thumbprint on the mirror, right? Or, don't, the key thing is going to be don't contaminate Hubble.
Right.
So that, that you reduce its scientific quality. And so designing a mission based on Dragon that lets you do that, I think is going to be a challenge, not by any means impossible, but there is going to be some new hardware and stuff like that they're going to have to come up with. So I'll be interesting to see. And then, so that's what the study's going to have to do. And then once that study is ready, then I think the discussion will begin on, okay, is this something we actually want to do?
And Rodney has a follow-up, and thank you for the super chat. Again, a Hubble reboost mission could be combined with or followed by a servicing mission?
Yeah, although that, again, is a lot more difficult, right? For a reboost mission, you just go onto the grapple fixture and, you make a secure connection. You don't have to, open up the doors. You don't have to get near the mirror. You just have to boost in the right direction. If you're going to do a servicing mission, right, okay, now you have much more worries about contamination because you're getting your fingers in, your spacesuited fingers in, and all the little connectors. There were a lot of them. Always the thing that breaks is not the thing that was designed to be replaced, or things like that. And so we're going. And there is. You close the lens cap before you get there, as Adam points out. But still, so I'm not so worried about really the main mirror, but the optics in the instruments, if you're sort of futzing with them, that's very delicate. So maybe you can do it. It's a challenge. It's a challenge that I'm skeptical NASA would allow with private astronauts. I could see a joint mission with NASA spacewalkers on the Dragon, so Jared and Elon do the kind of getting there part and the locking on part, and then NASA astronauts do the actual surgery.
Okay, interesting. Yeah, Eugene wants to know, could Starship possibly do Hubble service?
Well, again, it's the same issues, right?
Yeah.
It's can you approach it safely without contamination? Can you have the hardware? Can you add a robot arm to Starship to click it on? Alan says don't need Starship. I would agree. I think probably Dragon is a better fit than Starship. Just you don't need a huge great thing there. So this question that I see in the chat as well as I want to address is, am I happy that the UK is joining others in launching rockets? And yes, I am. As someone who grew up in England, it was always depressing how the UK was just not getting the space race. The government, the UK launched its first orbital rocket, but the government had in 1971, and the government had cancelled the program the month before because it was that was too futuristic, and we don't spend money on that in England. So finally, the UK space industry is a real thing now. And I mean, it's been there, but in terms of actually taking the lead in things like having launch sites, I think that's great. I think it's something for young people in the UK to sort of feel that they are part of the space age that they really haven't been able to feel until now. And so I hope, the UK is great at looking to the past and preserving the past, as we've seen in the last few weeks, right? It has all of this. It's very good at traditions. It's not so good at inventing the future. That's something that America, for all its faults, is much more home territory for America is let's change the future. That's not how England historically has thought. And so I think that a vibrant space industry in the UK will be healthy for England generally, and not just for the UK space industry.
Right. Awesome. Yes. And then George says there's 3 proposed sites across the UK.
Well, I think there's like 6, but how many of them are going to be real? Right. There's several in Scotland. There's a company called Skyrora that's trying to set up in the north of Scotland. There's a site in Cornwall, an airport in Cornwall that wants to be a Virgin Galactic or a Virgin Orbit rather site, and that's going to go operational very soon. I think there's another Scottish site in the Hebrides. I've sort of lost track of that. And so there's several options, and some of them are more real than others. So we'll see. It's hard at this. I think, clearly the Cornwall one is going to happen. Virgin Orbit's ready to launch in weeks, I think. Whether it will be successful enough to, they launch 1 or 2, or are they going to launch, 1 a month for many years? And that's the question. The Scottish sites, they're taking a while to ramp up, but I think they'll happen. I think that's going to be very interesting to see.
Irfan wants to know, how likely is a meteor to be dangerous?
Right. Well, the normal meteors, the little shooting stars you see in the sky, phew, like that, not at all. Right. Sometimes you see these really big fireballs. There was one over the Midwest recently, I think, and they're like chunkier pieces of rock that are hitting the Earth's atmosphere that can actually survive pieces of them to the ground. But it's still, I mean, by dangerous, if it hits you on the head, you've got problems. But if it lands right next to you, you're fine, right? It's not, and so you scale up, right, from that to the objects that are half a mile across that could wipe us all out. And it's just, the usual rule in astronomy is there's a lot of little things and a few medium things and a very few big things. And so the ones I mostly worry about are the ones like the meteor that came in over Chelyabinsk a few years ago. And if you haven't seen the YouTube videos of those, you should see it. This enormous fireball came in over Chelyabinsk, Russia. And fortunately, it blew up in the air, exploded in the air, and it shattered windows, throughout the city, and the blast wave collapsed the roof of some buildings and things like that.
Didn't it injure like 1,500 people?
Yeah, I mean, most, because so here's the thing: when you see the bright thing in the sky. Do not rush to the window to look at it, right? Stay away from the window, because when the blast wave comes, the window is going to shatter and fill your face with broken glass. Okay,
you guys, don't go to the window.
Yeah, that's the trick. And so that's right. There were serious injuries from that, but not, it wasn't like major catastrophe as it easily could have been if it had survived to the ground and actually hit made a crater in the city. And so I think there is a chance that in the next, in our lifetimes, say, there will be a meteor that will cause catastrophic damage to a city, right? Whereas I don't think, or at least to a city neighborhood, I don't think, the likelihood of something much worse than that is very, very low. So I'm not so worried in our lifetime of we're gonna have a dinosaur ending meteor that's gonna kill us all. Right.
I'm curious. I live in the Cascadia subduction zone here, and we're overdue for the big one, this big earthquake. And it just seems like there's so many things that are like we're overdue for. So what are you most?
Oh yeah. Earthquakes, volcano, absolutely. No, earthquake, big quake definitely is up there on the most likely, catastrophic thing that's going to happen in the next, 20 years or something.
Okay.
I would say super volcano eruption is less likely.
Okay.
Maybe on a 100-year timescale that can happen. I mean, certainly big volcano, not so likely in the US, but we've seen them other places, and they can cause weather like nuclear winter type stuff for a couple of years or something like that if you get a big enough one. And so those are I think up there, the sort of geological stuff, as opposed to the astronomical stuff.
Interesting. So you're more worried about that than us being wiped out.
Yeah, on our lifetime time scale.
In our lifetime. Oh, okay.
I mean, it's all it's all about time scale, right? Like what is the thing that's going to be the thing that you should worry about in the next million years versus in the next 100 years versus in the next 10 years, and those get different answers.
Well, let's turn the conversation a little brighter. I know that you have to get back to work soon, but what is it that you're most excited about or paying attention to the most right now, personally?
Well, let's see. What am I looking at right now? I mean, I think I have been focused on DART. I thought that was very exciting, and clearly, SLS and Starship, whatever my concerns about them are, is they require a lot of attention. They're very interesting, and they're very important. What else is coming up? I think the Chinese space station.
Okay.
A lot of interesting stuff going on there. They just did this crazy thing that's a copy of what the Russians did on Mir in 30 years ago. Is that they had the two main modules docked, right? And then they used a robot arm to unberth one of the modules and turn it through 90 degrees. So that the station is now flying through space L-shaped. It sort of looks like there's a bit sticking down and a bit like that. So it's like this really weird shape. And the idea is that this month, it's October already.
Oh my God.
I hate that. Later this month, another module is going to come up and dock where the old one was. And then it's going to move through 90 degrees. And then you'll have a T-shaped station that's more symmetric.
Okay, wow.
And this is exactly what the Russians did with Mir. The Chinese are basically copying it. But it shows there's a lot of activity going on there. And they've been doing spacewalks to outfit the thing. They've been using a robot arm to assemble things. And so they're really now ramping up their space activities. So I think that's something that hasn't had enough attention.
Yeah, I agree. Someone wanted to know, man, it might be way down there in the comments. Who do you think is going to get to the moon first? Let's see where the comment was. Yeah.
US from China?
Well, China or other state-sponsored.
Yeah, I don't think China's in a big hurry to put astronauts on the moon. I think they'll get there probably in the 2030s. Okay. But there's not like a crash program to do it.
Right.
So I think, presumably the US will get back there first if, SLS isn't a complete disaster. So we'll see. But yeah, I think the money has to be on the US at this point, and exactly what configuration and whether, there's a lot still to go to we don't have a lander yet. The lunar lander version of the Starship doesn't exist yet. So you've got to have both SLS and Starship and lunar Starship working. So we're a ways off, but I think China is even further off. Yeah, I don't think there's really a big race going on, is the honest truth. There's other countries starting to ramp up, but not at that level. So I think one thing interesting is going to happen is that India is going to launch its first astronauts on its own rocket into orbit. So they're going to do their Yuri Gagarin thing basically in a few years. Wow. And we'll see who else do we need to. I mean, I don't know. It wouldn't surprise me if some other countries start ramping up at that level. But yeah, China is the other state to look at right now.
Yeah.
The Russian space program is collapsing.
Yeah.
They're hosed. They really are in so many ways.
Yeah.
Right. What we're seeing in Ukraine, I think, is just the death spasm of the old way of Russian triumphalism. We just got to cross fingers that it doesn't end in a nuclear spasm, but otherwise, 10 years from now we'll see a different regime in Russia. But I think their space program is just, I don't see any way it can continue at this level it has been doing.
Well, Jonathan, thank you so much for joining. It's been a little over an hour. We've had at one point almost 200 people watching, which is great because I was worried with the early time that no one would be available to watch. So thank you guys so much for joining us, and drop a comment if you want more live streams like this with Jonathan. Hopefully Jonathan's open to that. I think he is. Yeah. But thank you so much. Is there anything else you want to say before we hop off and let you go get some lunch?
Lunch, what a great idea. Yeah, I knew there was something I needed. No, it's always great to chat with you, Ellie. Congratulations on the success of your channel and on meeting Elon. Yeah. And I look forward to chatting with you again soon.
Awesome. All right. Well, great. Thank you, everyone, for joining us this morning, lunch, afternoon, wherever you are in the world. We will see you soon. Thank you.